Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Today's webinar is titled Passenger and Freight Rail Systems Are Being Compromised by Climate Change: How Proactive Data-Driven Engineering Can Help Owners Adapt. Our Executive Director, Dr. Daniel Other, will serve as the moderator and will introduce our speaker today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon at the bottom of your screen. We'll do our best to address each question throughout the presentation. Before we get started, Dr. Other would like to say a few words. Dan, how are you?
Hi, Marissa. I'm glad to be here and to join our audience for what I know will be a webinar that stretches our thinking into new areas. Brought to us today by Academy patron Stanley, today's webinar explores the interface of something that we may be forgetting to think about, namely the relationship between the realities of a changing climate and the infrastructure systems upon which we all depend. In today's case, rail systems. Academy programming like today's webinar are a major benefit for membership in the American Academy of Environmental Engineers and Scientists. And many of our programs, including our webinars, are partially underwritten by the contributions of our patrons. So as we begin today's program, I want to take a moment to say thank you to our patrons. These are utilities and firms who financially support the Academy. As I mentioned at the start, I'd like to offer a special thanks to Stanley, who began the relationship with the Academy a number of years ago through sponsorship of individual webinars. You see, our webinar topics may be proposed by anyone, and each proposed topic is vetted by our webinar committee for relevance to our membership. We also invite individuals and organizations to financially support webinars, and Stanley stepped into this role providing $1,000 each for 4 webinars per year. After a couple of years of watching the success of the program, Stanley decided to step up and join as a patron of the Academy, providing $8,000 in annual financial support. If your organization would like to know more about how to propose or sponsor a webinar, please let us know. And if you'd like to learn more about the Patrons Program and to follow the lead of firms like Stanley and utilities like the rest of our patrons, we're here to listen to you and answer any questions you may have. And with that preamble, today I'm thrilled to join you to moderate what I know will be an exceptionally informative webinar on what some of you may consider to be somewhat an out-of-the-blue topic. We'll be hearing about passenger and freight rail systems and how they're being compromised by climate change. In particular, how proactive, data-driven engineering can help owners adapt. Why do environmental engineers and scientists need to be aware of this important emerging topic? Well, because the realities of a changing climate have impacts on critical infrastructure. These impacts are real, and our profession is well suited to understand these challenges, to design, deploy innovative solutions. Today's presentation will be offered by Jake Hellman, who's a principal consultant at Resilient Analytics, a Stanley Consultant company. Jake holds a bachelor's in civil engineering from the University of Pittsburgh and a master's in architectural engineering from Colorado Boulder. He describes himself as somewhere between an engineer, a climate scientist, a data analyst. While I can't speak with any authority to this self-description, I can say Jake is super smart, working on some great problems, and I can't wait to hear more in today's webinar. So it's truly my pleasure to introduce Jake in this webinar. And before we begin, I just want to give a quick reminder. Please put your questions in the Q&A function, and I'll use these as part of a moderated discussion at the end of the webinar. And today we're going to do something a little bit different as well. Jake would love to pause in his presentation and help take any questions. So please be thinking of your questions throughout. Drop them in the Q&A, and as Jake pauses, we'll address some of your questions as we go through the webinar. And now, with those instructions, Jake, the stage is yours, my friend. We're excited to hear from you.
Okay. All right. Thanks for the introduction and thanks for having me. My name is Jake Hellman. I'm a principal consultant at Resilient Analytics, which is a Stanley Consultants company. And we're going to be talking about passenger and freight rail systems, how they're compromised by climate change, and ultimately how a data-driven engineering approach can help owners adapt. So before we get started, we can talk about the agenda. So first, we'll talk about climate impacts on engineering in general, and then more specifically, climate impacts on the rail system. We'll talk about how we can address these climate impacts in engineering through a data-driven approach. The third item will be a combination of those two. We'll be applying that data-driven approach to resilience in the rail sector. And then finally, we'll wrap it up with other applications of the data-driven approach. So first, who is Resilient Analytics? For reference, Resilient Analytics is a Stanley Consultant company. Before that, we were a research institute out of University of Colorado Boulder. We really started with a data-driven decision support for resilient infrastructure. We've worked across a full spectrum of assets. We always prioritize a proactive versus reactive assessment where we can find out return on investment and really starting to prioritize other adaptation strategies. Fully based in engineering design, we started as a group of engineers who got into climate science and not the other way around. In general, Resilient Analytics is a multidisciplinary team made up of engineers, planners, climate scientists, and data analysts. In 2016, we were incorporated. We had over 30 peer-reviewed publications. We've been on peer-reviewed committees. And in 2022, we were acquired by Stanley Consultants, who is now our engineering wrap. So now we have an end-to-end approach to resilience where we can identify vulnerabilities to climate, recommend adaptation strategies within design, and even implement those. So over the last 18 years, we've worked with a number of different clients all over the world. There's me. I joined in 2014. Clients range from the United Nations to private companies, such as Haynes. We've worked in over 115 countries. We've done work with DOTs, state entities, utilities, you name it, including higher ed and local communities as well. So we will get right into climate and engineering design. Climate has always been a factor in engineering, as everybody knows, whether it's wastewater treatment inflow, looking at precipitation frequency curves, or retention pond, thinking about wet and minimum evapotranspiration years. And historically, we've always designed infrastructure to look at past climate conditions, because that's all we had. We looked for the last 20, the last 30 years. We saw what's the wettest year, what does this precipitation event look like, and then project it forward. And climate modeling is starting to change that narrative. Now we have projection data, we have more information that can help us build the infrastructure of the future for future conditions. So not only can we address design, but we can also address the impacts. So we've modeled baseline conditions. We've looked at the 100-year peak discharge in a channel, but now we can begin to model projected conditions. We can look at acute risk, which is damage from a catastrophic event that might be from a hurricane or a wildfire. We can look at operational risk, which is more chronic to infrastructure and ops. Shortened pump lifespan would be a good example. And ultimately, through an approach that we'll talk about later, these impacts can be modeled and quantified to inform decision-making, because that's what it's all about. It's about quantifying these impacts, finding the magnitude of that, and then seeing if adaptation can help add resiliency for our communities and the infrastructure it serves. Specifically for the rail system, I think the FRA specifically calls out resilient infrastructure, and they talk about hurricanes, tornadoes, extreme precipitation, and extreme heat specifically. Extreme heat is probably the most well-known impact on the rail system. Every summer, there are news articles talking about delays in Amtrak or freight or anything, whether it be a big heat wave in the Northeast or the West Coast, whatever it might be. And that is ultimately because extreme heat can cause delay and damage, buckled rail, derailment, and heat restrictions get put into place when the temperatures get warm enough, which leads to that delay. And that leads to secondary impacts. That could be supply chain disruption, which goes to construction or operational materials. That could be treatment chemicals, steel, whatever it might be. And there are also environmental impacts. Air quality from idling, potential derailment impacts could be a big one as well. And ultimately, what we do know is that heat impacts rail, and we also know that heat events are projected to increase. You can see on the map, which is a map that was provided by LocaViewer. Loca is a type of climate data that we'll talk about later. It's looking at days over 95 degrees. This is where we would see speed orders be put into place. This is the change in days, and that ranges from about 20 days to as high as 80 days annually, which is a huge difference. So we'll see more of these delays We could see more of these damages, but ultimately we can turn this risk into an opportunity. And the market has started to see that owners and operators and builders are taking notice and want climate change to be addressed. It's not an abstract concept anymore. It's appearing in RFPs. And ultimately, as engineers, we need to be prepared for this, and it needs to be done correctly. So we can, engineering companies, engineering firms need to act as a trusted partner with owners and ultimately decide how to understand these risks and implement this as a new risk metric. So how can we address climate impacts in engineering? And we have a data-driven approach that we take to resilience. This is a framework that we utilize in order to make actionable results and informed decision-making. And you can see on the left-hand side, it is a very quick diagram of how we do this. We'll go into each one of these steps in more detail, but it's collecting and processing, and then the key being connecting the data. So when I say connecting the data, I mean, we have all of these data streams and we need to connect it to infrastructure. We need to create stress response functions. We need to estimate damage and cost in some way. And then we produce that model, we interpret that data, and then we apply that data in some way to create actionable results. So the key to the data-driven approach is to gather a number of different data types and connect them to infrastructure, which is easier said than done. So let's take a look at data collection and data types. Data types, these are the 7 main ones we work with. They vary in sources, in format, in size. They're updated constantly. In today's world, data is constantly being produced and it can constantly be utilized. So the first one and probably most important one is climate data. So climate data is starting to be integrated into engineering and engineering design. Many of you are aware that the new NOAA Atlas 15 actually includes climate projections, and that's just one example. So climate data can come from a number of different sources, whether it be public or private, and we'll get into some of the specific sources that we use later in the presentation. So spatial data is another data source that we use. So that would be climate data is gridded, which is not incredibly useful for interpreting the data. So going from a gridded resolution to county or city or state boundaries, this is a geospatial process. So spatial data is important. Physical data would be tree canopy or impervious surfaces or floodplains, things that would impact the sensitivity perhaps to a certain climate impact. Infrastructure data is pretty straightforward. That would be, in this case, for this example, the rail geometry, the length of the rail, and other infrastructure data attributes such as rail traffic and things like that. The fourth one, methodological data. This is that connecting piece. That would be stressor response functions, really that connection between the data sources and the infrastructure. The impact data, this would be data that could be monitored by the owner or operator. So the number of buckling events would be an example, or the number of failures in the past from some event, things like that. And then finally, cost data. We prioritize quantifying these impacts financially. So unit costs and finding not only the cost of damage, but of other impacts like delay and secondary impacts like that. So after we collect the data, we need to process that data. And really that data can be pretty raw. So it needs to be cleaned. You need to fill gaps. You need to produce more data, perhaps. You need to evaluate the data, which is important, and ultimately format that into the final input data to the model. So this seems like a pretty simple process, but this can be incredibly tedious, especially with the large data sets. The climate data, for example, that we use is, at least the one we pull from usually, is well over 50 terabytes. So making sure and evaluating that climate data is really important. Filling in gaps from whether that be rail or road data sets or whatever it might be, where there could be at a district level differences in how they input the data, and ultimately getting into the final format so we can process that data and connect it to the infrastructure. As I mentioned, the connecting piece is probably the most important part. This is connecting all of those data streams, establishing the analytical structure, establishing the stressor response functions, which are the response of the infrastructure to the climate in a certain area. It is going through the model boundaries and assumptions. A lot of assumptions need to be made on these. depending on how generalized or specific the model is. And then ultimately, we need to establish the data that needs to be produced. Derived climate variables is a good example. Climate data is, in its rawest form, maximum temperature, minimum temperature, precipitation, and some other variables, which isn't so helpful. We need more specific variables, such as the depth of the 100-year, 24-hour rainfall event, things like that. And then the cost scenarios, which would be reactive or proactive, ones that include adaptation strategies or not. And then finally establishing the final metrics, which drives the narrative for interpretation. And this is an iterative process, as you saw from that first one. It's going, and you can go back and collect and process data and connect it to infrastructure until you have what you need ultimately to start producing this model. We model in a number of different environments: MATLAB, Python, ArcPro, and these can be output and integrated into more traditional engineering softwares, the hydraulic modeling system being one. And this is an iterative process and includes a lot of sensitivity and validation. Because we're working with so much data, those two things are incredibly important. And then interpreting the data. So establishing categories. Are we looking to see how the impacts might change over time? Are we seeing how it might impact across asset types? Spatially, perhaps certain districts or states, or locally, certain assets specifically, and synthesizing these results to create succinct data. We're creating way too much data to interpret it all, so we have to create a summary to establish key trends, patterns, and insight to make it actionable and apply it to deliverables such as vulnerability assessments, resiliency improvement plans. We've done engineering resilience assessments, creating technical reports, and all of these things include asset vulnerability and risk. We can include project prioritization, which can be woven into capital improvement plans or long-range transportation plans. We can look to changes in design standards, and these deliverables come in a ton of different formats depending on the climate, whether it be a report, GIS, interactive tool, and it has to be consistent with other initiatives. And this is really important. Communicating with the client and the owner what else they're doing as far as capital improvement plans or within resilience planning to make sure that this isn't put on a shelf, to make sure that these results are actionable, which means that they are custom, they're put in their terms, they're speaking their language, they can be included in their operations. They are cost-driven, meaning that we have quantified impacts and we have quantified adaptation strategies. And ultimately, it gives them all the tools they need to make an informed and familiar decision. So quick summary so far, before we get into a pause for questions. Climate impacts engineering, design, and infrastructure. Heat can cause damage and delay in the rail system, and heat events are projected to increase. A data-driven approach utilizes all of these data streams to create actionable data by connecting the data to infrastructure. And then finally, a data-driven approach can help quantify sectoral impacts of climate change, which we'll talk about later. And that specific example is going to be rail. So quick pause for questions here.
All right, we had a few that came in the chat, but I've also got a few to throw in here. So Jake, one question. What's the difference between climate and weather? Is there such a thing? Do we need to worry about that semantic? Can you help us understand that?
Yeah, that's a good question. So climate is essentially the long-term pattern of weather. Weather would be singular events looking over the next 7, 14, maybe 2 weeks, where we are looking to see how specific events are going to impact us. It's more operational, I will say, when thinking about it in this sense. Climate is looking over long periods of time, 20, 30 years, and seeing how these things will change in the long term.
Okay, and a couple other quick questions, particularly on precipitation. One question came in, are you looking at a total annual rainfall? Are you looking at particular events and the intensity of them, or all of the above?
Yeah, you can look at all of the above, and it depends on what you want to look at, really. So the climate data itself can be daily or sub-daily in some cases. So you can look at sub-daily and daily precipitation events. So you can certainly look at precipitation estimates for the 100-year, 24-hour, or even the 100-year, 2-hour in some cases. There are some limitations, I will say, as you go sub-daily, right? These are, climate models that are projecting to 2100. So obviously, when you get into hourly things, then, the uncertainty starts to grow. But in other cases, you can certainly look at annual projections, and some climate metrics such as drought or wildfire indices look over longer periods of time, especially drought. We're talking about, the 12-month precipitation of evapotranspiration trends. So
Perfect. And then last, final quick question, right? Do you run all the models from raw data, or can you guys take output from one model and dump it in as input to the other? And how do you manage that? Because it's the difference between getting all the raw data and getting various pieces that other people have run. Is there a balance that you try to work out there?
Yeah, absolutely. We have familiarity with a lot of data sets. So we have data sets that we can always default to. But when working with a specific client, I will say we try and utilize as much data as they can provide us, because that's the most useful for them. So it is a mix. We are certainly data analysts, and we have expertise in pulling together a number of different sources and making them speak to one another. And that is a huge part of what we do. So
awesome. Thank you so much.
of course, thanks for the questions. Okay, so transitioning into a data-driven approach to resilience in the rail sector specifically. So we'll be applying now this approach. So we're going to talk about a project that was done with the EPA. This looked at impacts across 22 sectors, which included rail, roads, and bridges. You can see on the right-hand side, there was a number of different sectoral impacts, including air quality, West Nile virus. We focused on infrastructure, roads, bridges, rail, and Alaskan infrastructure. Today, we're talking just about rail. So the goal of this was to enable cross-sectoral comparison as well. So looking to see how certain sectors could be impacted by climate and comparing the magnitude of that impact. So this was designed to estimate the physical and economic damages to the United States under different climate scenarios ultimately. And specifically for rail, which is a huge industry, there are 140,000 miles of Class 1 rail. It is an $80 billion freight rail industry. Passenger carries $30 million people annually. It is not a surprise that this was included in this analysis, and it is not, as we talked about before, surprising given that rail is susceptible to damage under extreme heat events. And as we mentioned, climate change indicates an increase in the number of these extreme heat events. So once we're getting that impact and we put that side by side with an $80 billion industry, we can start to see some pretty big impacts. So we'll walk through each one of the steps to the data-driven approach. We'll walk through each data source as well. So we'll walk through each of these 7 in more detail and go through and we'll stop midway through right before the connecting piece. So we'll start with collecting. So the climate data, this was consistent with CIRA. So this is an example where they actually provided us with the climate data. It was 5 representative models. It was 2 representative concentration pathways, which are emission scenarios essentially. So in the bottom right, you can see that figure, which looks at a change in mean annual temperature across the US. So RCP 4.5 is a middle of the road scenario from an emission standpoint compared to RCP 8.5, which is a high emission scenario. You can see under RCP 8.5, the mean annual temperatures are greater than RCP 4.5. So those were essentially 10 scenarios that we are running across. For this analysis for rail, we use daily maximum temperature because we were only going to quantify extreme heat. That was given to us in NetCDF format. And although the data set only included 5 models for 2 RCPs, oftentimes we run 32 models for 2. It's still 1.2 billion data points. It's still a huge data exercise to get this from daily maximum temperature to ultimately the metrics that we needed. So the next data source is spatial data. The native resolution of the climate data grid is a 1/16 of a degree, about 3 miles by 3 miles. But we needed to get that into something easily interpreted and consistent with ultimately what the EPA wanted, which were national climate assessment regions, NCA regions, and that can be converted by a weighted average, summed across. So there's some geospatial processing in that. The infrastructure data in this case is the GIS files that looked at the length and geometry of the Class 1 rail. It included the track rights, which is used to estimate passenger versus freight, and the volume, which was from the federal highway rail crossing data set. So there was 152,000 unique crossings that had daily rail volumes. You can see the image on the right-hand side speaks to the number of unique crossings. This is in Denver specifically. And then the methodological data. This is not how you would traditionally think of data. This could be just looking for reports, literature reviews. In this case, on the right-hand side, it was the risk analysis for track buckling safety, which was done by Andrew Kish, who was a part of the US DOT, track buckling prevention theory concepts, Federal Rail Administration. There was a lot of work done by the Volpe Center, which is National Transportation System Center, and trying to find the current operating procedures and then other equations to make those connections, to connect climate to infrastructure. So we have ambient temperature, but we need to get to rail temperature. We need to calculate the stress-free temperature of the rail, which is the design neutral temperature. That is the temperature in which the rail has no internal stresses. It's the temperature in which it's laid in the summertime. The expected buckling probability, which is pretty complex, and even delay. So on the bottom left, you can see the railroad heat restrictions. You can see it differs by railroad operator, difference by temperature. The restriction speed is also different. So going and collecting all this data is imperative to the analysis. The impact data, so for this specifically, looked at buckling data for validation. We were trying to calculate the expected number of buckles, and we needed to ground truth this somehow. So we pulled data, we'll talk about it a little bit later, we pulled data from the UK. There was not specific data on buckling events from heat in the US, so we had to look elsewhere as that ground truth. Cost data, so there's a number of different cost scenarios that we looked at, but it came from RS means, it came from guidance from the US DOT as far as delay goes. We had to split business versus pleasure, bulk versus intermodal unit cost, which is two types of freight, ultimately intermodal being, bulk would be materials, things like that, intermodal shipping containers, and then the cost to the crew, the cost to the public, and then the cost to repair. So there's a ton of different assumptions we have to make, which was guided by US DOT, like 6% of the total trips were considered to be business trips, for example, and all of the ratios in between. So this was based off of a methodology by Lovett et al. 2015, which looked at the estimates of cost of delay for freight trains and the railroad company and the public. So processing this data. So cleaning this data, we had to go through and only include class 1. We had to include only operational track as well, eliminate all the rail outside the US. For filling gaps, we had to fill in missing volumes if a grid didn't have a volume by looking at the surrounding grids. And then we had to produce other data like the passenger versus freight ratio. The traffic was not split up into passenger versus freight at each node. So we had to estimate that by looking at track rights. Evaluating that data, doing a sanity check. What are the traffic volumes in rural versus urban? What is the climate metrics that we're using across? Are we seeing differences in the baseline where we would expect to see that, things like that? And then finally, formatting, putting them in grid level tables for reading. This analysis was done at a grid level ultimately. So before the second pause for questions, quick summary. So the rail analysis was designed to estimate physical and economic damages of climate change. Rail is just one of many sectors that was being looked at. The rail system is a massive industry, and ultimately the climate impacts were suspected to be pretty large. And then this analysis was meant to quantify that. Finally, a ton of data sources had to be collected and processed before we even begun this analysis.
Awesome. We've got some more questions that have come in. People are really engaging with this, Jake. Really appreciate it. So one was about a specific data set, right? So the American Society of Civil Engineers and NOAA are working on, there's some data sets out there like the Atlas 15 for precipitation. You're thinking about intensity, duration, and frequency. Is there a similar system being put together for temperature? Are you aware of that? Is NOAA working with anybody, something that's available?
There are some tools that I've seen that have some high-level indicators, I will say, at a national level, but Atlas 15 is probably the first and biggest initiative that we've seen that is kind of at this national level that is being passed down to engineers. So we have always found that often we are going through and doing those derived climate variables for something specific, right? For whether it be like pump lifespan or, really something that an engineer on site might know, or that has been monitored by the client, for example. But so there are some high-level resources, but those can be hard to interpret and might not be specific to your site, right?
Sure. No, fair enough. And then the second one, of course, we're worried about loss of life. We're worried about the economic impact of travel time. We're worried about the loss to environment when the derailment or spills occur in the area. So are you looking at these over kind of like, miles of track? Are you looking at them at particular sites? Because I imagine like potential damage to the local community might be a whole lot bigger if it's a spill of something hazardous in a town versus in the middle of nowhere. So how does all that stuff start to relate together?
Right. And this is a really good question about just the level or the scale of this analysis. This particular example is pretty generalized. So we're looking at all rail within a grid, and we are not really thinking about the local community. We're also, as I'll mention later, not quantifying derailment because that's an incredibly challenging thing to do and to estimate, right? So these are just costs for delay. These are just costs for repair and not even thinking about derailment. And that's sort of that next step, right? This is a high level policy of, okay, what's the magnitude here? What could the potential impacts be at a cost level? And then we also do really specific site related items. And that could be one of them, right? What if this does happen, if we're thinking about derailment, working with a local railroad owner and working with Amtrak, whoever it might be, trying to think about, okay, this is where I'm vulnerable. This is where a derailment cannot happen due to a vulnerable community. And then connecting those two pieces, which is outside the scope of this project, but it's a great call out.
All right, great. Thanks, Jake. Appreciate it.
Yeah. So next we'll get into the connection of the data and we'll talk about the cost scenarios that we laid out, right? So this was establishing the analytical structure. CIRA, which is the EPA study, laid out 3 scenarios. One is no adaptation. The second is reactive adaptation and proactive adaptation. So for no adaptation, this is actually a step back from what current operators do. And this was just to be consistent with CIRA. So this would be, there are no blanket speed orders, which is different from what is being done today. What if we just let rail run regardless of the temperature? What would happen? We would expect to see a large number of buckling events and we would have to replace that track and there would be delay associated with that. So those are the 2 cost scenarios for that. It's the replacement of that track and the delays from a track buckling. The reactive scenario is current operating procedures. So these are delays from blanket speed orders, but we also know that track buckles, right? We know that there are still buckles, so there is still a cost to replace that track, and there is still delay associated with that. And then finally, there is proactive adaptation. In this case, we are estimating the cost of installing sensors, which can help to give a risk-based speed order. So it is a different type of speed order that was proposed by the US DOT through some of those literature sources that I talked about previously. And so these are delay, but in a different form, and we'll get into some of that. So things that were not included, we did not estimate derailment. We did not talk about routine track maintenance. We are only looking about extreme heat, and this just had to do with a lot of the scope of work and some limitations, right? We just didn't feel comfortable estimating derailment from buckling events. We just didn't feel confident enough in that connection. Although we could expect some of those things, it was not included here. And as I mentioned before, this can be an iterative and parallel process to the first 2, collecting and processing that data. Second part of connecting, we'll get into just a few of these stressor response functions. So expected buckling events, this is the crux of how we estimated the number of buckling events. So as temperature increases, there's an exponential curve, which this was developed by the US DOT and through some of that research. The higher the temperature, the higher the probability of buckling and the more expected buckling to occur. It is also a function of the length of the trains, the number of trains, and the frequency of the temperature itself. So For reactive delay, this would be the blanket speed order. Delay was estimated using the reduced speed versus what the base speed would be, the length of the trail, and the hours of the speed orders. And then for proactive delay, this was this risk-based approach where instead of a blanket speed order, which is done, as you saw from that table earlier, where it went from 80 to 50 just over a certain temperature, this is thinking a little more, I'll say, to a localized level of what are the specific track conditions, because we have this sensor network, and what is the speed in which the allowable temperature reduces this risk enough to this equation on the left. So it is a more informed decision, and it is a risk-based decision. So ultimately, the delay or the restriction might be less, or it might not be enacted, because we know that the rail temperature is not vulnerable ultimately. So also connecting, we established the boundaries. So we looked at 20-year eras in 2030, 2050, 2070, and 2090. All of this was consistent with CIRA. We scaled up to a 0.5 degree resolution, which was chosen, which just to better represent ultimately the rail stock. And the baseline time period was from 1950 to 2005. That is a limitation of the climate data itself. So we looked at an undiscounted cost and a 3% discount rate consistent with CIRA. And we also adjusted costs based off population and GDP growth, which you can see on the right-hand side. And that was another initiative of CIRA. And as I mentioned, we did not quantify derailment, but there were a ton of other highly specific assumptions, like what is the hours of the delay from the speed order? What is the hours that the train is in service? What is the freight speed restriction for the blanket speed order? What is the passenger speed restriction? And that was based off of that table we saw earlier. So finally, the data to be produced. We had derived climate variables that we needed. We needed to turn daily maximum temperature into restriction events. We needed to know when there would be a blanket speed order in order to estimate that delay. We needed to know the average max summertime temperature, which feeds into calculating the stress-free temperature. And we needed to know the minimum allowable and maximum temperature for expected buckling, and ultimately the probability of temperature for expected buckling. And these are calculations over those 1.2 billion data points. We're going from daily to annual data sets specifically for this piece of infrastructure, because we identified these stressor response functions are based off of these secondary derived climate variables to calculate rail temperature, rail stress-free temperature, and buckling is associated with stress-free temperature. The lower the stress-free temperature, that means it is a delta above that temperature. So the lower the stress-free temperature and the higher the temperature, the worst case scenario it would be. And then we're also calculating the risk-based speed reduction. So instead of just a 30-mile-per-hour reduction, we're estimating it based off the temperature. So a 5, or let's say a 35-degree day, you would be a speed reduction of 5 miles per hour versus a 35 degrees Celsius day, which could be 15 or 20 miles per hour. And then the final metrics are delay minutes and costs from buckling events and repairing events, and also the blanket and risk-based speed orders, as well as investment costs for the proactive scenario. So all of that connecting has to now be produced. So in this case, the model was 1,500 lines of code. It was written in MATLAB. There are 10 scripts and functions. And there's a ton of iteration, right? We were taking a ton of different data sources. So QC was imperative. Over 50 runs were saved looking at various items and testing the sensitivity of some of the broad assumptions, such as the time of flow order, the train speed, and the restrict temperature. Sensitivity in these types of generalized models is huge, right? You're looking to see, okay, if I change the train speed baseline from 80 to 70, what might happen? You'd expect minimal changes or changes that might be, linearly correlated. But if you see something much larger, that means we have some other issues within the model that we go in and we iterate and we find, and we go from there. And then finally, the validation, right? So this would be comparing the output to something we've seen and something that we can ground truth against. So in this case, we used buckling events per mile. So we estimated buckling events per miles for the reactive approach, which is current operating procedures, and compared it to a source from the UK. And ultimately, that was within 15%, which is pretty good for a generalized model. And obviously there are differences between climate in the UK and here. So we took a representative region to estimate that even more specifically. And then the second thing was for the no adaptation. If you don't do anything, if no one restricts speeds at all, you do get more buckling events, a lot more buckling events, and it's 70% higher than what we would see, which is just a good sort of sanity check of, okay, the model is behaving how we think we are. It is being ground truth, and all of this checks out. And then we can kind of move on to the interpretation. But another pause for questions. Summary so far. The rail analysis is rooted in research from the FRA and the US DOT. The analysis looks to quantify 3 cost scenarios: no adaptation, reactive, and proactive. And then finally, the sensitivity and validation are critical to this modeling process and the modeling success ultimately.
Awesome. Great. Well, the question that came in here. So what are some of the preventative industry measures that could be working on this? Are there like changes in rail tie connectors, alloy composition?
Yeah.
And maybe that's leading into your next section, but that seemed like the right question to ask at this point.
It's a great question. I will talk about a number of different adaptation strategies that are currently being implemented. When we started this study, it was very limited. And this new sensor research that we proposed was also new, and it's now starting to be integrated. So we'll go through a number of those different adaptation strategies, but it is important to call out, we only modeled one proactive scenario, right? And by no means do we think that the entire rail network should implement a sensor network across the United States. We understand that that's not feasible. The point is to provide a justification for proactive adaptation, just to give a quantification of, okay, how much could I save if I got collaboration between all of these rail owners and operators? And then at a local level, yeah, maybe the adaptation strategy is a little bit different, right? But from a modeling kind of higher level policy model, which is what this is, we just looked at one. So, yeah.
Great. Thanks.
Yeah. Okay. So last few itims here. So interpreting, this is incredibly important. So now we have produced all of this data, and now we have to interpret it. So we have spatially, what does it look like? So you can see the maps on the right-hand side. Where are the hotspots? The Midwest, not surprisingly, where we see a lot of rail traffic and a lot of rail lines, looks to be an area that experiences some of the highest costs. You can see over time from that top row 2050 to 2090, you can see a slight darkening of these maps, meaning the costs are higher, which would be expected. And by scenario, under the higher emission scenario, where the temperatures are higher, we see higher costs. So establishing all of this criteria, creating succinct data, and then looking at the key trends. So this is a figure showing a representation of how those costs increase over time. And these are pretty significant increases. You can see that baseline estimate where we're only looking at a few $1 billion annually. And then that scales up to a wider range, as much as 10, ranging down to about 3 million or billion, sorry. So key insights. 1, there's a large increase in costs under all scenarios. So the no adaptation shows a huge increase in buckling events, delay, and costs. The reactive adaptation scenario shows a large increase in speed orders, not surprisingly, because there'll be more restriction events, but does help to offset the buckling events, which means that the current operating procedures are certainly helping, which is not surprising because we would expect them to be doing this for a reason, and we know it is somewhat effective. But compared to the proactive adaptation scenario, the risk-based speed orders can dramatically reduce that delay cost by making more informed decisions using that sensor network. And in general, the highest costs were in the Southeast or the Midwest, but you can see up that table, the proactive adaptation scenario can save billions of dollars annually. And that is over the long run. So there's an initial investment cost that would set you back a certain number, but by 2050, we're already receiving a pretty big return on investment. And then interpreting across sectors. As I mentioned before, this is just one of the 22 different sectors. So rail compared to others nationally was the 9th highest from an economic damage standpoint, which makes sense. It's an $80 billion industry. And it was also the fifth highest reduction when comparing the two emission scenario, meaning that under the higher emission scenario, it is 36% higher, which is a big difference, right? And that went to a policy level of if we reduce greenhouse gases, if we aim to cut more, then we could save on some of these impacts. So looking more locally, or I guess from a regional perspective, we can see that in the northern plains, which is in that lighter blue, we see that rail is actually the third largest economic impact compared to other sectors and fifth in the Midwest. So in certain regions, it had a much larger impact relative to other sectors, which is another important finding. So for the application or applying all of this from a data-driven approach, we ended up creating a number of different deliverables. One was the actual CERA report and writing those chapters. We had 2 publications as well, one in transport policy and one in climatic change. And then finally, there is a framework for evaluating damages and impacts, which is called FREDI. And this is a framework for the EPA to allow local users to pull some of this data in order to estimate these sectoral costs at a different level. So this is enabling this data to be utilized by others and can be utilized for local adaptation plans, climate action plans, resiliency improvement plans, things like that. So data structures were provided to them, technical reports, and that included this vulnerability and risk. It included benefit cost analysis and ultimately some adaptation policy. So taking a step back, what does it mean? What are the high-level takeaways? So one, not surprising, climate change will have a big impact on current rail operation. We saw costs increasing a lot. We saw that direct result of delay from extreme heat events, and extreme heat events are increasing. And that is $1 billion annually for an $80 billion industry, which is pretty significant. We see that the current operating procedures are relatively effective in reducing those buckling events, right? Which is a safety feature, right? So although some of those costs for reactive are pretty high, we would be saving potentially in some of those derailments, which those costs weren't quantified. And then finally, probably most importantly, proactive adaptation can save owners billions of dollars. So this is justification to invest. So proactive adaptation that we've seen. So in its simplest form, you could paint the rails white, and we've seen this. We've seen this done widely in Europe. Painting the rails can lower the temperatures 5 to 10 degrees Celsius. It's been done in the US, the Transportation Authority of Rye, New York. The issue with this is you have to do this annually or every 2 years. So it can be pretty expensive. There are other research into passive temperature controls, which you can see in that middle image. And this is a device that's attached to the track to mitigate temperature spikes. It absorbs heat from the rail, and it has been tested and can reduce the maximum temperature by as much as 20 degrees C. But implementation can be challenging. This is more, this was research that was being done by the FRA and the US DOT. And the third one is reinforced foundation, right? So you could put concrete slabs that can contain the higher forces, but it's incredibly expensive. So it's like 4 times as expensive as a standard ballast track. So although it can be effective, that justification can be challenging for an owner, given that it is 4 times as much. But we're hoping that results from this show that it still could be justifiable given the cost that you would, I guess, inherit otherwise for a rail operator. And then finally, what we modeled is a rail sensor network. So there are products out there that look at predictive rail temperatures. There are systems looking at live temperatures, which looks to local track conditions. So maybe you don't need a blanket speed order across an entire region. Maybe you just need speed orders on certain areas of track in an area where the temperature is higher and there is no shade. And And then the predictive rail temperature monitors think about the temperature and the sun angle throughout the day in order to make more informed decisions. Maybe the blanket speed order doesn't need to last 10 hours. Maybe it only lasts 5 hours, things like that. And then finally, there are stress-free monitors and longitudinal stress monitors, which look at the stresses within the rail, which can find weaknesses in the system and then ultimately lead to more maintenance in that particular area. So these are just a few of some of the proactive adaptation that we've seen. Amtrak has implemented some of these networks. There are other rail operators that have done this as well. So other applications of this model and the data-driven approach as a whole. So the rail model was also applied to work with the Canadian government and the New York State Energy Research and Development Authority to quantify these impacts and justify some adaptation. So that is an application of this model specifically. But in general, this framework, this data-driven approach can be applied across all sectors and all scales, right? We looked at a national level study specifically just for rail, but we've also done work with the Arizona DOT, for example, where we looked at one site, SR88, which is a historic state route that was damaged by a flooding event, and we gave design recommendations for culverts and drainage that was included in a design concept report to improve this road's resilience ultimately. So that is a site level analysis. So we can go from a site level to a national level, and that's the beauty of this framework and this data-driven approach. You can look at specific engineering design at a specific site, or you can look at a policy level. And in between, so we've done work with the Water Utility Climate Alliance, where we were looking across 5 different water utilities, thinking about worker health and safety, and all of the assets and weaving some adaptation strategies into their long-range plans. And in Hillsborough, we did some adaptation recommendations for a number of assets to be included in their long-range transportation plan. So that's just a few examples. And as I mentioned, you can apply this to essentially anything you want. Climate impacts almost everything. And from a physical asset standpoint, it does impact everything. You just need to put all the pieces together, and all of those pieces are spread throughout all of these data streams. So you need to be able to connect all of that data to infrastructure, model it. You need to be able to talk to clients. You need to be able to produce data that is actionable. So summary overall, last slide, a data-driven approach can help streamline, connect, and produce actionable data. We want data and we want results that are going to be included in decision-making. We want project prioritization. We want to get funding opportunities perhaps for resilience, which is a lot of the work that we do. And there's a lot of data, and it's constantly being produced. So you need experts that can go and get that data and interpret that data and be aware of these data releases. And then when applied, the data-driven approach showed that there are big impacts to rail operation. The operating procedures are effective. Proactive adaptation can help owners save billions. And more innovative technologies will help mitigate the impacts of climate change in the rail sector and elsewhere. So when thinking about climate and when thinking about its impact on infrastructure, I implore all of you to think about how changes in some climate or weather variable could add or impact your infrastructure, and how resilient strategies could help mitigate those impacts to climate change. That's it. Thank you so much. Looking forward to the questions and discussion.
Awesome, Jake. That was fantastic. That maybe if we stop the slide share, then people will be able to see our smiling faces. I don't know. Maybe they don't want to see our smiling faces, but we can have a little moderated discussion here. Thanks so much. So got some questions that appeared in the chat, and I've kind of put some stuff together. What I'm going to do is I'm going to kind of run through the laundry list so that you can kind of get your mind around, and then we'll come back and hit them kind of a second time. So starting with kind of like some background and large view, right? Like British Rail has been in India and in the UK, a really hot and a not so hot place for quite some time, right? So to understand what do we know historically, why not just build everything to deal with the hot temperatures that we know are there at the equator around the world? So that's kind of a first background question. Long-term policy implications, right? As these warmer temperatures move further north, right? And we do these retrofits. When I saw, hey, we're going to paint these lines white and we do it every 2 years, the environmental in me said, well, that paint goes somewhere. So, those remediation efforts are going to have environmental impacts. So will the idea of certain routes being more likely to derail might change where we can send hazardous materials and how we transport them. So there's some specific environmental portfolio related to these policies. Transferability, right? So how about maglev or other type of rail systems? How about other infrastructure cracks in pavement? And you're looking at time delays associated with this. I could imagine repavement could go along with cracks, could go along with delays in transport. So I can imagine that at a 40,000-foot view, there's some analogies that could be applied to other systems. So some transferability. Early on, you talked about the importance of being trusted. One of the things the Academy is all about is board certification, which is a credential to show people to be trusted. So maybe speak a little bit to how do we show folks that they should be trusted in this kind of brave new world of a new type of engineering science that we haven't done a lot with before. You talked about this idea of funding sources and it's preventative work, right? So somebody's got to pay ahead of time. What's the space look like there that felt like part of what you were doing was data that would then go into a business plan argument for why to make investments? So if you can speak to how does the work fit into that? And then to our students, emerging professionals, people that are looking for second options, things to get into, what kind of background, what do we need? Like, this is not the standard, here's the textbook, go to the odd number problems at the end of the chapter and do them for homework kind of job that you've got here. So we'll conclude with that, those kind of words of wisdom. So, way back up at the top, the first one kind of background, right? So British Rail, India, British rail system, UK, British rail system, plenty of heat, plenty of sun in India, less so in the UK. They somehow over 150 years have had rail, plus in all those places. Why not just build everything for where it's hot and is there a cost there? Yeah.
Yeah. So the interesting thing about rail and the system is, one, the construction is incredibly simple. And one of those simplifications is that the rail stress-free temperature is relative to the location in which the rail is placed, meaning the hotter the location, the higher the stress-free temperature, but the higher the projected temperature will increase, right? So it's actually the delta that's more important, because when you put a rail down in the UK, right, it's stress-free temperature, and what you're aiming for is the maximum summertime temperature, because there's also contraction, right? You can't just put it down and say, we're going to have this for a 110-degree day, because then in the wintertime, it'll contract and once again cause some issues, right? So the stress-free temperature needs to be somewhere between those two things. So it's actually the differentiation or differential between minimum and maximum temperature. So it's relative to the location, if that makes sense.
Totally makes sense. So it's not that it's just either really hot or really cold, it's that it swings back and forth. So in Missouri, where we have all 4 seasons in one day, we've got the worst kind of problem. So,
Yeah, right.
So long-term policy implications in the relationship to environment. You talked about some remediations that could be done, some ways to pull some heat away, some ways to reflect heat. We're looking at derailments and rerouting. So particularly for us in the environmental profession area, what are some of the impacts that we might be needing to explore when you're doing these retrofits? Any ideas? Are people starting to explore those?
Yeah, this is really interesting and kind of talks to the higher level communication between engineering disciplines, right? Where one adaptation strategy that can help this infrastructure could also have other downstream or secondary impacts. And that's why it's so important for all engineers to understand this, understand why we're doing this, and come up with strategies that perhaps have less impacts, right? So, the impacts, and you mentioned like the painting of rails and things like that, which is really interesting, right? I'm sure some people are prioritizing the rail delay over some of those environmental impacts, but it is incredibly important to have that sort of collaboration when implementing these sorts of things.
Perfect. And any idea, have you seen anything in your searching, right? Because I mean, we would transport some hazardous waste on rail. We'd be worried about what line. And so have you seen anybody exploring this, or have you run across anything where folks are saying like, here's regulations for transport based on derailments?
Yeah.
buckling and
Yeah, logistically, and the rail system is also interesting because it's owned by essentially 7 operators who operate differently but share track, and Amtrak is somewhere in between them. So there is definitely differences just between how they all operate, and they all use their own sort of sets of line. I think there are adaptation strategies that Amtrak has started to implement some of these sensors, but I don't know if I've seen any sort of logistical changes of rerouting because of extreme heat events, things like that. And you know, maybe there would be, but oftentimes I think it's kind of business as usual, right? That's just a part of their business plan, and this is sort of that sensor network and how that can help, right? And I think as these rail operators also get a better grasp of data and big data, they'll start to collect this, and there'll be sort of live logistics where you might be avoiding some of these things. So
makes sense. Makes sense. Big industry, so money to be made on not having
sure,
delays. So that makes sense.
sure,
So how about transferability? If we would think about maglev rail as opposed to, kind of
yeah.
what we've got here in the States, or we think about some of these folks moving to high speeds, et cetera. And yes, any thoughts, any ideas there?
Yeah, so it is interesting because this, for rail specifically within the US, it is freight, but there are passengers, but there are alternatives that could alleviate a lot of these things, right? And off the top of my head, I don't know exactly how maglev could be impacted by climate. I'm sure there is some way, but my guess is it could have added resiliency benefits. So it is interesting, and the rail industry it's a bit odd in the sense that it's old and it's owned by 7, but transferability, yeah, I think there are a ton of innovative solutions that will come out. And especially if we start seeing more and more delays from a passenger perspective, there'll be more investment because people will be looking beyond Amtrak and maybe into some other alternatives. So
Yeah, no, I just saw a meme of a $20 trillion tunnel from New York to London. So
right, yes, that would be a great option. Yeah.
It's an interesting option. Cracks in pavement, asphalt, and then the relationship between delays from
Yeah.
repairing roads. So that's another
Right.
high level transferability. But
Yeah.
are you able to borrow from that kind of literature, or do you see a literature there?
So we quantified that exact thing in this study for roads. So we looked for roads across temperature impacts, flooding impacts, freeze thaw, and precipitation. So we looked across those 4 stressors and quantified the damage to road and what it would cost to repair that. And part of that was construction costs. Hey, this road is down from a flood, but also, hey, instead of 60, you're not going 30 for the next 2 months, right? And thinking about just the disruption costs. So we have quantified those things. And in the same exact process that we just went over here, we went through connecting all of these pieces, the stressor response function for, when it is over this temperature, or what's the design temperature for this binder grade? Do we cross that? If we cross that, we're going to expect some damage. What is the time and cost to repair that damage? And then what is the time and cost to invest in a higher quality binder grade, for example, that could offset that? So yeah, similar approach. And we did that for bridges. And like I said, you could really apply this to anything if you can sort of think through how climate impacts whatever infrastructure piece you're looking at. Yeah.
No, it makes sense. Seems like there's a lot of transferability there. So how to be trusted in this space, right? This is, we've had some other webinars where we're kind of in these, frontier pioneer spaces, right?
Sure.
And it's kind of like, all right, so how do we tell the difference between the snake oil
Yeah.
salesperson and the trusted, hey, I actually have something you should invest in?
Yeah, totally. I think one is just looking for past work, right? We were rooted in academia, so our integration into the private industry was interesting because we started in peer-reviewed studies, and we were starting in committees that were looking at our work and validating our work and making sure that happened. So I think that's the first thing. And I think the second thing is just looking to see that a team is multidisciplinary, right? There are a ton of firms that look at climate projections, but might not understand it through an engineering lens. And that's why we have this multidisciplinary team where we have engineers and planners and climate scientists all working together, but have really specific focus on, okay, let's evaluate the climate data here, just so we know that it is, representing the climate well, it's representing this derived variable well, before we can even apply it to the infrastructure, which is connected through the engineers and the data analysts and understanding all that, right? So, I think it's working with people who have just a ton of experience within resiliency and within data itself. So,
okay, makes sense. And then, one of the things you talked about is the funding, right? So it felt like that part of this study was being done almost like to build the business case for a sensor network, which kind of made sense. And if I misunderstood that, correct me. But
no.
but if you're trying to do, if you're spending money to prevent having to spend money in the future, it feels like a difficult sell, not an impossible.
Yeah.
So how do people that are listening to this, how do they frame that so that they can make the investment?
Totally. Talking to the owners is a challenge here, right? And one of the ways that we've done it is, one, talking about how you can quantify these costs, proactive versus reactive, right? And having an understanding of, we've done enough work that we sort of know in what areas we think we can get some of that return on investment. The second is federal and state funding specifically for projects, right? Which can help to cover those costs. So protect funds, which I'm sure everybody is aware of from the bipartisan infrastructure law, gives money for a number of different bins. But one of those buckets is planning, which is looking at resiliency improvement plans. And if you have a resiliency improvement plan that prioritizes projects, then you can get more federal funding. Basically, the non-federal share can be reduced, right? So that helps, right? And I think it's up to 10%, right? So by creating some of these resiliency improvement plans or thinking about resilience in infrastructure, it unlocks some federal and some state funding. And then there is just funding for some of this work in general, right? So that helps. And protect specifically is for the investment, right? So if you were redoing a bridge, for example, and you would rebuild the bridge, but that we're going to see increased flow underneath that bridge in the next 30 years, and you would expect some of that damage. Protect funding can help you unlock additional funds to build that bridge even higher. So some of those things wouldn't be covered, right? Because we're already doing this work. But an additional however many millions of dollars is going to be added to this project to make it more resilient. And there are other programs beyond just Protect. So.
No, perfect. So students or folks that have been working for a while that are looking to train up and see this as a new opportunity or see this as an emerging space, what advice would you have for them? What background do they need, right? Besides being good at staring at data.
Yeah, of course. I think just being familiar with resiliency as a whole, right? And understanding what ASCE is doing, or federally what resilience programs, and going into case studies and looking, whether it be from DOTs or whatever other agencies. There's been a ton of work on resilience that includes climate. So I would implore everybody to go and read through those, see some of these processes, look at some resiliency improvement plans, which will help you understand even more how climate science can be applied to engineering. And then I think as you're going through, and whether you're in the design or whatever phase of engineering you are, you're going to see some design standard and think, I wonder if this is going to change. And that's exactly what we're looking for, right? And then there could be some added resilience piece to that. So the goal is for every engineering project to think of climate as a new risk and understanding that as some new risk. So I would implore everybody to just read. There is a ton of work out here, although it is not so mainstream. There's a ton of work in the resilience space, in the ASCE, DOTs, whatever it might be. So I implore everybody to go read through that. And then national studies like CERA sort of quantify larger sectoral impacts that we talked about today. So
any other countries or any other organizations globally that you would also pitch to people that you would say, hey, wait, if you're going to be looking at this, I mean, obviously there's ones we would think about here in the States, but anything global countries?
Yeah, I mean, there is, and even outside of engineering,
sure,
Europe has done a ton of work just on like the private side. So private companies have been looking at how businesses are being impacted by climate. So I think even extending over there. So looking to the EU, they are certainly ahead of, so the European Union Commission has done a ton of work in this space, similar to work that the EPA has done, more policy level. And then all the way down to, like the Deutsche Bahn has done a ton of work in rail. You can look across Europe and sort of see their resilience efforts, which in a lot of ways is actually ahead of the US.
Okay. Okay. So those would be some good examples as well for people to look at.
Yeah.
Fantastic. Any other advice you'd like? Free opportunity for you to share with folks?
No, I think that, we think this is incredibly important, and we're just excited to get in front of you folks. So thanks for having us, and thanks for letting us talk about climate and engineering. We think it's incredibly important, and we hope that you keep this in mind as you're going through your engineering careers. So
No, it's fantastic. If you want to throw your slides back up, I believe
yes,
one person was asking for your email, and I think it was there on the slides at the end. I believe you've got the slide that Melissa
yes,
needs to close us out.
let's
So maybe.
do.
Yes, and I think the email's also in the chat.
Oh, wonderful. All right. Well, I think he's got his slides up, and I will say, Jake, thank you for joining us. We really appreciate having you
Yeah,
here.
absolutely.
Thank you.
Thanks so much. Bye-bye.
Thank you, everyone, for all your questions, and thank you to Jake for sharing your knowledge with us today. We do have several webinars planned in the near future, so you can go to aaes.org/events and reserve your spot. Just a reminder, if you're not yet a member and you're considering joining the Academy, please email me to discuss our membership options. PDH certificates for this event will be sent out shortly to board-certified individuals. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.